Hi everyone, my name is Serena Lau, and for my CS 131 or Discrete Math presentation, I will be doing it on Bayes' theorem. So first off, what is Bayes' theorem? Bayes' theorem is a tool that we can use to help us determine the probability of different events. This can include the following: the accuracy of a medical test, the likeliness of randomly choosing a green ball from a blue ball in a bag, and many more. So to derive the formula used as Bayes' theorem, we have to look at two important relationships. That is, A given B is the same thing as A intersect B divided by B. Similarly, if we switch A and B around, we can get almost the same equation, which is B given A is equal to B intersect A divided by A. But now if we look at the numerators of both of the equations, we can tell that they are actually the same. A intersect B is the same as B intersect A. So if you think about it in the sense of like a Venn diagram, no matter what you put on the left or the right side, whatever they intersect, whatever they have in common, will always be the same. It doesn't matter which order you read it in. So knowing this now, we can multiply out the denominators from both sides so that we can get the equivalent. So now doing that, we have A intersect B, which we also now know is the same as B intersect A, is equal to both A given B multiplied by B or B given A multiplied by A. So we can now divide both sides by P of A to get B of A, or B given A, sorry, which is equal to A given B multiplied by B divided by A. Looking at a different relationship, we have A is also the same thing as A intersect B union B complement. So B union B complement will give us one full set, and once we intersect that with A, we will still be left with A. So now using distributive property, if we multiply A by both B and B complement, we will end up with A intersect B union A intersect B complement. Putting that together, we have that equals A. Now we can put those in terms of P of A, and so now we can use that so that we have this equation, and once we substitute A intersect B using the relationship from earlier, we can substitute that for A given B multiplied by B. And doing that same thing with A intersect B complement, we have P of A is equal to A given B multiplied by B plus A given B complement multiplied by B complement. So now with these two parts of the equation that we derived, we can put them together now. So looking at the denominator of the first equation and our second equation underneath, we notice that they're the same. So we can substitute this out so that we get our full Bayes' theorem equation. So this will leave us with B given A is equal to A given B multiplied by B divided by A given B multiplied by B plus A given B complement multiplied by B complement. So now that we have the equation, we can use it in real life situations. So here's one of the examples that we have. So suppose that 8% of the patients tested in a clinic are infected with HIV. Furthermore, suppose that when a blood test for HIV is given, 98% of the patients infected with HIV test positive, and that 3% of the patients not infected with HIV test positive. What is the probability that? So we have four different scenarios, and that is, we can split them into two sets basically. So the first set is going to be that they test positive for HIV. And in that set, we're going to have two situations. So either they test positive and they do have HIV, or they don't have HIV. The second full set that we're going to have is that they test negative. But if they test negative, there's two chances that they can either really be infected with it or they are not infected with it. So here we have two sets. So think about it how I mentioned earlier with the complements. So the first one would be they're not infected, or sorry, they are infected with it, and the complement of that would be that they're not infected with it. So looking at the data again, this is what it means. So A just means that that just represents the patients that do have HIV. That has nothing to do with whether they tested positive or negative. It just means that they do in fact have HIV. And among those patients, we did see that there were 8% of them that had the disease. And then another piece of data that they gave us were the patients with HIV that test positive. So that is B given A. So that just means that given that they have HIV, or given A, they test positive, or B. So patients without HIV that test positive, or B given a complement, that is 3%. And then, so this is just a reiteration of what we're trying to find. We're trying to find patients that test positive with HIV, patients that test positive without HIV, and then the opposite, patients that test negative with HIV and without HIV. So to find A given B, or the patients that test positive with HIV, we can see our equation right here. All of the information was given to us. So we're just plugging that in. The only thing that we really did have to find was a complement, which was basically 1 minus 8%. So a complement union A is just going to give us one full set. So that's how we find it. So B is just going to be, or P of B is just going to be 0.106. And so that's not going to be our final answer, but we do use that to find A given B. So there's our equation right there, and we just plug everything in to get 74% for A given B. Now to find patients that test positive without HIV, or A complement given B, we're just going to find that in a similar way, as it is going to be a full set. We just have to subtract our first percentage from 1, and we do get 26%. Okay, so a new question that they have are patients that test negative with HIV. So this is going to be A given B complement. So we have our equation again. This one looks a lot more similar to the full version of Bayes' theorem, or the final equation that we did use and that we derived. The only thing, let's see, what did they not give us? So a lot of the things here weren't given. The only data that we did use directly from the problem was A, and that was 8%. The other ones we did have to find by just finding its complement and subtracting it from 1, or subtracting it from the full set. So that's how we got 1 minus 0.98, or B complement given A. And also the same with B complement given A complement, which is just 1 minus 0.03, and the same thing with A complement, like we found in our last problem, 1 minus 0.8. So after plugging all those numbers in, we're going to get 0.002. And similarly, like our second problem, this is just going to be a complement of the previous problem. So A complement given B complement will just be 1 minus the percentage that we just got. So 1 minus 0.002 is going to give us 0.998. And so that's all I have for today for my presentation on Bayes' theorem. I hope you enjoyed. Again, my name is Serena Lau, and today my presentation for CS 131 was on Bayes' theorem. Thank you.